Okay, and welcome back to the next video for Math 150. We're now going to continue talking about some rules of probability, and specifically we're going to look at what we call the additive rule of probability and the multiplicative rule of probability. So we're going to start you off with the definition, and this definition talks about two events being mutually exclusive. So if we have two events that are mutually exclusive, that just means, or a series of events that are mutually exclusive, that just means they can't happen at the same time. Examples of mutually exclusive events. You can't both pass a test and fail a test at the same time. You either have to do one or the other. So those two events are considered to be mutually exclusive. You can't both wear an all red shirt or an all blue shirt at the same time. Those two events are considered to be mutually exclusive. So assuming that we have two events that are mutually exclusive, then the probability of the first event occurring or the probability of the second event occurring is equal to the probability of the first event occurring plus the probability of the second. So really what that tells us is we want to find the probability of a first event or second event or a third event or a fourth event or a finite amount of events. Assuming that all of these events can't happen at the same time, then we just add up their probabilities. So let's take a look at a few examples using the additive rule of probabilities. Well, our first example here says if you have a full deck of cards, find the probability that you draw a king or a queen. Well, let's take a look at this. First of all, I hope you understand that it's clear that if you draw a card from a deck of cards, that it can't be both a king and a queen. So drawing a card is mutually exclusive. So these two events are mutually exclusive, which means the probability that you draw a king or the probability you draw a queen is the same thing as saying, we'll find the probability of each event and then add them together. Well, if we have a deck, a standard deck of cards, and the standard deck of cards, a total of 52 cards, then, excuse me, the probability that we're going to draw a king from that deck of cards is 4 out of 52. Right? We have 4 different kings in the card, 4 different suits. And similarly, the probability we draw a queen is going to be 4 out of 52. So that gives us a total of 8 out of 52. Now, if we were going to express that as a decimal, 8 divided by 52 is equal to 0.154, rounded to 3 decimal places. In this example here, we're going to round all these to 3 decimal places just to be a little bit different. Okay, so again, the reason that that works is because these two events are mutually exclusive. You can't draw a card that's a king and a queen simultaneously. Let's take a look at another example. If you have an urn with 3 red, 2 orange, and 5 black marbles, find the probability you draw an orange or a black. Okay, so first of all, in terms of how many marbles we have altogether, we have 3 red, 2 orange, and 5 black, so we have a total of 10 marbles altogether. So I hope you can see that we're going to be dealing with a denominator of 10. So the probability we draw an orange or a black marble is the same thing as saying, and again, let's go back and check and make sure that these two events are mutually exclusive. Well, if we draw a marble, it can't be both orange and black at the same time. Right? It has to be either orange or black. So that means that these two events are mutually exclusive. And that tells us the probability of drawing an orange or a black is the same thing as saying the probability of drawing an orange plus the probability of drawing a black. Well, okay, we have 10 marbles altogether. So we know the denominator is going to be 10. The probability I draw an orange, well, 2 out of those 10 are orange. So that's going to give us 2/10. Excuse me, the probability I draw black. Well, again, out of those 10 marbles, 5 of them are black. So we have probability of 7 out of 10. And as a decimal, that is exactly the same thing as saying 0.070. There's a 70% chance of drawing either a red or a black marble, excuse me, an orange or a black marble. Okay, let's try another example. Now, what if two events are not mutually exclusive? I want to draw a picture for you and make sure that you understand that. That means that these two events can occur at the same time. So here's my first event. We'll call this event A. That's that guy over here. Here's my second event, which is event B. And these two events can occur at the same time. So they do intersect at a certain point. So if we want to figure out the probability of A or B, well, the probability of A represents this guy over here. the probability of B, let's let B represent this guy over here. And I hope you can see that when we consider the probability of A or the probability of B, that we actually hit this intersection twice. We hit it in A and we hit it in B, which means that, again, assuming the two events are not mutually exclusive, so they can happen at the same time, the probability of event A or B is the probability of A plus the probability of B minus the probability of A and B, or minus one of their intersections. So that way, when we sum together these two probabilities, we're not hitting that intersection twice. We have to remove one of them. So to find the probability of A or B, if they're not mutually exclusive, we can find the probability of the first event. We add that to the probability of the second event, and we subtract from it the probability that both events occur, the probability of A and B, or the probability of those two events intersect. Well, let's take a look at the example below. The probability that Jamie will wear blue on Monday is 0.37. The probability that Jamie will wear white on Monday is 0.26. The probability that she will wear blue and white is 0.12. So here's an example where these two events are not mutually exclusive because she can wear both of them. Maybe she has a checkered shirt that's blue and white, or maybe half the shirt's blue or half the shirt's white. Whatever it is, these two events are not mutually exclusive because it's possible for her to wear both of them. So find the probability that she'll wear blue or white. So the probability that she wears blue or white equals the probability that she wears blue plus the probability that she wears white. Excuse me, there should be a P over here. Plus the probability she wears white. And again, because it's possible for these two to intersect each other in this example, then we're going to subtract off the probability of blue and white. Okay, so the probability she wears blue is 0.37. The probability that she wears white is 0.26. The probability she wears blue and white, so we're going to subtract off that intersection, is 0.12. So the probability that she wears blue or white, well, when we add those two together, 0.37 plus 0.26 minus 0.12, and that gives us a probability of 0.51. Okay, well, let's take a look at another example when we're dealing with two events that are not mutually exclusive. And again, all that means is that it's possible for the events to happen at the same time. So for this example, if you have a full deck of cards, find the probability you will draw a king or a hearts. Now, again, it's kind of implied here that you have an understanding that these events are not mutually exclusive, but I hope you can tell that it's possible for you to draw a card that's both of them on your first try. You can draw a king of hearts, so it's a combination of both. It's a king and it's a heart. So these two events are not mutually exclusive. So that means when we want to find the probability of king or the probability we're drawing hearts, that's the same thing as saying the probability you draw a king, ooh, sorry about that, plus the probability that you draw hearts, what does my beautiful heart's not looking at, minus the probability that you draw a king of hearts, so something, a king and a heart. Okay, well, the probability you draw a king, and again, in a standard deck of 52, we're going to have 4 kings. So that's 4 out of 52. And the probability that we draw hearts, well, in a standard deck of 52, a quarter of them are hearts, or 13 of them are going to be hearts. So that's the same thing as saying 13 out of 52. Okay, and then minus the probability that you have a king and a heart. Well, there's one card in there that's going to be the king of hearts. So that's going to be minus 1 out of 52. Okay, so to sum these up, the denominators are all going to be the same at 52. 4 plus 13 is 17. 17 minus 1 is 16. So we have 16 out of 52. And 16 divided by 52, rounded to 3 decimal places, gives us 0.308. So 0.308. Okay, and again, this is if you hear the word or. Anytime you hear the word or, I want you to think the additive rule of probability. So or means addition. And we're going to compare that to one more rule of probability in a few minutes. But let's take a look at one more example here. The following chart represents favorite food from a group of 102 people who all belong to a local soccer league. And you remember we saw this question before. Now what I wanted to do is I wanted to show you how we can apply the additive rule of probability to it. So this said, find the probability a randomly selected person will select pizza or pasta. So again, you hear the word or, and I want you to think to yourself the additive rule of probability. So the probability of pizza, I'm just gonna draw a picture of pizza. There's some pepperoni on it. Or pasta, let's draw some pasta. And these events are mutually exclusive. You can't choose pizza and pasta at the same time. So that's the same thing as saying the probability of pizza plus the probability of pasta. Okay, so the probability of pizza, well, we know there's 102 people altogether. The total amount that chose pizza was 17 plus 5 or 22, plus the total amount that chose pasta was 23 plus 19, which is 42. So we have 22 plus 42 out of 102, which gives us, let's see, 64 out of 102. And again, we're rounding these to 3 decimal places just for fun. 64 divided by 102 gives us 0.627 as a decimal. Oops, sorry about that. Let me rewrite that. 0.627. And similarly, let's compare it with the example underneath that says, find the probability a randomly selected kid will select sushi or pizza. So now it's a randomly selected kid, so it's not a person, right? I mean, kids are people, you know what I'm saying. We're not looking at the entire sample space here. We're just gonna focus on children, right? And so for children, we have 17 plus 23, which gives us 40, 40 plus 8, which gives us 48. So our denominator now is going to be 48. And the probability a kid will select sushi or pizza. So the probability of sushi, I'll draw a little sushi roll here, or pizza, let me draw a little pizza, equals, well, the probability that somebody likes sushi, that a kid likes sushi, excuse me, is 8 out of 48, plus the probability that a kid likes pizza. And again, remember that these two are mutually exclusive. That gives us 17 out of 48. That gives us a total of 25 out of 48. And again, rounded to 3 decimal places, 25 divided by 48. That gives us a 0.521. Okay, so again, you hear the word or. I want you to think to yourself, anytime I hear the word or, I am dealing with this notion or I'm dealing with this idea of the additive property of probability. And so we're going to talk about one more property of probability, and that is this last one over here. This is what we call the multiplicative rule of probability. Here's how the multiplicative rule of probability works. If you have 2 independent events, and when we talk about this idea of independence, that means the outcome of one event does not affect the outcome of the other. We're going to talk more about that in a second. But if you have 2 independent events, then the probability of A and B is the probability of A times the probability of B. Okay, so anytime you hear the word and, most of the time, I shouldn't say anytime, but most of the time when you hear the word and, when we're dealing with probability, I want you to think of the multiplicative rule for probabilities. So this idea that the outcome of one event does not affect the outcome of the other, that means that the sample space is not going to be messed with. The sample space is left alone. And I want to compare that with 2 events that are dependent, where we say this idea that the outcome of one event affects the outcome of the other. And so in dependent events, if A and B are dependent events, then the probability of both of them occurring, the probability of A and B, is the probability of A times the probability of B given that A occurred. So when we're talking about this idea, the sample space is affected. The outcome of one event relies on the outcome of another event. So let's do this. I want to make sure that you understand, I'm going to make this a little bit bigger to make it easier to write with. I want to make sure that you understand what I'm talking about when I say the sample space is affected and the sample space isn't affected. And something that we can look at here is this word with replacement and without replacement. So when we replace something, you put it back. And specifically in this example, you reach into an urn and you draw 2 marbles. If you have an urn with 3 red, 2 orange, and 5 black marbles, find the probability you'll draw an orange marble first and a red marble second with replacement. What that's telling us is we're going to take the first marble, we're going to look at it, then we're going to put it back in the urn and then draw the second marble. So the sample space is still a total of 10 marbles for both pools. Right? You pull out the first marble, you look at it, you put it back. You pull out the second marble, you look at it, and you put it back. So we're replacing the marbles so the sample space doesn't change. This is an example of independent events. Well, let's compare that to 2 events that are dependent. Well, here we're looking at what it says without replacement. So it's the same exact question, but this time I'm asking you what happens without replacement. So, sorry, you reach into an urn, you draw 2 marbles. If you have an urn with 3 red, 2 orange, and 5 black marbles, again, it's the same question. Find the probability of drawing an orange marble first and a red marble second without replacement. So what that means is you're going to pick up a marble, you're going to look at it, and you're not going to replace it. So now instead of having 10 marbles, now you only have 9. So the sample space is effective. So this is an example of dependent events. The probability that you draw a red second depends on the fact that you drew an orange marble first, and we're not replacing them. Okay, so sample space is not effective when we talk about with replacement. Sample space is effective when we talk about without replacement. Now, you don't have to worry about this. You just need to know that whenever you hear about with replacement, the sample space is going to be changed a little bit. So let's take a look at this example. You reach into an urn and you draw 2 marbles. Find the probability you draw an orange first and a red second. So this is the same thing as saying the probability of orange times the probability of red. Okay, well, what's the probability we draw an orange first? Well, of the 10 marbles we have a total of 10, 2 of them are orange, right? So if we draw an orange one, we have a probability of 2 out of 10 of them being orange. We look at that marble, we put it back in. So the second pool, when we pull out the second marble, we still have a possible total of 10 marbles. So what's the probability now that our second marble is going to be red? Well, if we take a look over here, we have 3 red. So this is the same thing as saying 2 over 10 times 3 over 10. That's the same thing as saying 6 over 100. And as a decimal, that's the same thing as saying 0.06. Well, let's compare that first. Let's compare that with this next one. This says the same exact directions, except this time we don't replace them. So the probability of an orange times the probability of red, well, it's going to be the same thing, except it's the probability of orange for the first pool times the probability that our second one is a red, given we drew an orange in our first try. Okay, well, let's take a look at this first bit. What's the probability we draw an orange? So again, we have an urn. Inside the urn, we have a total of 10 marbles, and 2 of them are orange. But now I take that orange marble, right? So this guy over here, we have 2 orange marbles. Now I'm going to take that orange marble and I'm going to throw it away. It's no longer going to be in my urn. So I'm going to have 9 other marbles, but of those 9 marbles, we know that one of them, of the 9 marbles that are left, only one of them is orange. So we have a total of 9 marbles that are left. Whoa, that is way too big. Sorry about that. Let me fix that. So what that means, now for the second one, well, okay, think about this. We have total of 10 marbles. 9 of them are left. How many of them are red? Well, remember, the first one we pulled is an orange. So we have 9 marbles left. So 3 of them are red. So this gives us a total of 6 out of 90. And when we go and do the math, 6 out of 90, rounded to 3 decimal places, is the same thing as saying 0.067. And that's it for the additive rule of probability and the multiplicative rule of probability. What I want you to remember is anytime you hear the word or, let's go back up here. Anytime you hear the word or, remember that we're dealing, or not anytime, most of the times when you hear the word or, we're dealing with the additive property. And when you hear the word and, we're dealing with the multiplicative property. Anytime we hear about this idea of with replacement, that means the sample space doesn't change and the events are independent events. The outcome of the first doesn't rely on the other. Anytime we have this idea of without replacement, so you take the marble and you throw it away, or you take the person, you kick them out of the room, whatever it is, then our sample space is changing. Then we have a little bit of a different type of probability because we're dealing with two events that are dependent rather than independent.